Okay, YouTube, in this video we're going to be discussing the properties of matrix addition and scalar multiplication. And just like real numbers have properties, for instance, some of these properties are the same as the properties with real numbers. But we know with two real numbers, if you were to add them, a plus b, you get the same thing as if you did b plus a. That's a property for real numbers just as it's a property for matrices. So what we're going to do is we're going to consider, instead of like the set of all real numbers, we're saying this is the set of matrices, and we want to know what kind of things can we do with these matrix things that we typically use uppercase letters for. I'm trying to write them in all different directions. There's A, B, C. Doesn't look very good, but essentially when you have the set of matrices, what can you do with these? We say the commutative property of addition holds. So basically it doesn't matter what order you add two matrices in, you get the same thing. And I suppose this would make reasonable sense, say if we added like 1 0 0 1 plus 2 1 1 3. It wouldn't matter if we did this in any order, because you could notice here that you're going to add these component-wise anyways, like 1 plus 2 is 2 plus 1, so we get 3. 0 plus 1 is 1, 0 plus 1 is 1, and then 1 plus 3 is 4. So you would get some new matrix here, but it doesn't matter what order you do this in. And likewise, we say associativity holds. That is, we could go do these two first. We could add b plus c first and get some new matrix. We'd call it D, and then add that to A. And you'd get the same thing as if you were to add matrices A and B first, and then add that to C. And keep in mind, when you're adding matrices, these all kind of maintain that they have the same order to begin with, okay? So when we talk about associative property of scalar multiplication, remember we're talking about properties of scalar multiplication. It says it doesn't really matter which you multiply first. You can multiply the two scalars and then distribute that throughout the matrix. Or you could take this D here and distribute it through the matrix, and then distribute this new scalar into that new matrix, okay? Scalar identity basically says 1 times any matrix is that matrix there. And the interesting thing about the distributive property is it works for both matrices and scalars. So if you were to distribute this through, we'd say, well, you could take the scalar times each matrix individually and then add that, or you could just add the matrices right up front and then use the scalar later. And then also this, it's kind of like saying if you had like matrices, you could just combine the scalars out front. So kind of like 2a plus 5a, well, this makes sense, that's 7a, that's all it's saying. So when we talk about using these things, basically what I want to do is now start evaluating these matrix expressions. And we know this is a matrix expression because it has no equal sign, so it's just a statement. Also, that these are capital letters, and that implies that they are matrices. So I've already written out what these matrices are up top. It says use the properties above to simplify the following matrix expressions, then check our matrix values using a graphing calculator, okay? So if we had a graphing calculator, we could put each of these in, A, B, C, and D. I would hope you would think that that would take longer to put in than it's worth. But we'd say, look, I'm adding each of these, which has 3 rows and 1 column. So A, 3 by 1 plus B, 3 by 1, 3 by 1, 3 by 1. We know we're going to get some new 3 by 1 matrix here, but if I were showing my work, we'd say, I'd write it out thusly. And we'd say, well, we've got these 4 3 by 1 matrices, and this is going to add up to this, final 3 by 1 matrix. And we say, okay, so 4, negative 1, 2, 0, 2, 0, negative 3, negative 1, negative 2, and then negative 3, 5, 2. And so we could just add these straight across, essentially, or we could do them in any order we wanted to. But we say 4 plus 0 plus negative 3, so that'd be 1. 1 minus 3 more would be negative 2. We say negative 1 plus a 2 is a 1. Minus 1 is 0 plus 5 is, itself 5. We say 2 plus 0 is 2. Plus negative 2 is 0. Plus 2 is 2. So we get this new matrix here. And so this is all we're doing is carrying out operations. So again, get expressions like, 2a plus b, the quantity a plus b. And the property here states that we could do this as 2a and then find 2b and then add these things together, and you would actually get some new matrix that we're after here. I hope that everybody, when we rewrite this, first of all, you want to rewrite this. And let me use a parenthesis here. We're saying matrix A, is 1, 3, negative 2, 2. And we are adding that to matrix B, which is this other 2 by 2 matrix, negative 4, 0, negative 3, 1. And what we're going to do is this. We say, well, what's more convenient here? To actually distribute this through and then add the matrices, or could we just add the matrices now and then double everything? And I think it makes more sense to actually do these first. So we get 2 times some new 2 by 2 matrix where we would just do what's in the parentheses. First we say 1 plus negative 4, is negative 3. 3 plus 0 is 3. Negative 2 plus a negative 3 is a negative 5. And then 2 plus 1 is going to be a 3 here. And so now we could just go ahead and scalar multiply this, and we would get negative 6 actually, positive 6, negative 10, and then 6. And this would be our new resultant matrix. But that's how you carry out matrix operations. Just be sure that you understand these properties and you know that they exist to your benefit. Cheers.